Hey guys, welcome in. Today we're going to do some simulation of space with Universe Sandbox. It's going to be very interesting to see all kinds of gravitational effects of planets and asteroids, things like that. There we are, a little dot here, just making a little rock orbiting around a little star, little gas ball, plasma. But that's where we are. It's just incredible. How do you look at this and go, oh yeah, I don't care? It's like, that's everything you know, everybody you know, every person you've ever met, all your family, all of your friends, every person who's ever lived, right? That's where we are, and it's just beyond amazing. There's our planet, Earth. So you can see there's Mercury, there's Venus, there's the Earth. That's just remarkable how we happen to be here on our planet where we can survive, and for billions of years we've survived billions of orbits around the sun. Through that time, all the species of animals and plants and every living being that's ever existed. It's just amazing. There it is. That's what keeps us all energized. That energy beams out into space, hits the Earth. The plants use it for photosynthesis. They produce sugars with it. We eat those sugars and we become energized. It's just amazing how everything works the way it does. It's just incredible to see and to understand how mysterious it is. Absolutely love it. So let's take a look at some simulations here. Here's the Milky Way. It's a barred spiral galaxy. The Milky Way has 4 spiral arms composed of hundreds of billions of stars. Now, if we get closer inside of the galaxy, you can see that there's a supermassive black hole here, the center. And you can see stars orbiting around the black hole. First of all, they're most likely very large stars, but more importantly, they're orbiting at millions of miles an hour around the black hole, supermassive black hole at the center. Pretty accurate when it comes to the speed or rotation speed of the galaxy. It actually turns out that galaxy spiral arms, even at the outer edges, they actually rotate fairly quickly, relatively speaking, when it comes to the center of it. This is because of dark matter. We know that dark matter, probably in the form of Webb particles, things like that, exists. We can't see it directly with our eyes, right? We can't see it with telescopes either. Light doesn't interact with dark matter, but dark matter permeates a lot of our galaxy, accounts for all that rotation as well. Because if we take a look at all the matter that we can see under light, all that regular baryonic matter, that doesn't account for why the galaxy's outer arms are spiraling so quickly. We need extra matter to account for that speed. So when we add dark matter into the equations, it works. That's what dark matter really is, and we can see it with gravitational lensing. Telescopes can, the light from these telescopes can be warped or look like marks, and this is what it means. That's the Milky Way galaxy. Just another galaxy. Hundreds, billions more out there. Here's the collision between Andromeda and Milky Way. Now, in about 4 billion years from now, our Milky Way galaxy will collide with the nearby Andromeda. It's unlikely that any stars in the galaxies will actually collide, although some stars will likely be ejected from the combined galaxy during the merge. Wow. So we're witnessing the collision of 2 galaxies right now. You can see them kind of merge together to this one super galaxy. This is 39 million years, 40 million years, so about 1 million years every second. A million years a second. You can see as it coalesces, it kind of takes into more shape over time. The 2 supermassive black holes at the center are likely going to merge together to form an even larger one. And that's amazing. So 60 million years after. Speed it up a little bit. Wow. So it even becomes more discombobulated, and then over hundreds of millions of years, it becomes another galaxy again. Probably an irregular galaxy, as we see many of those in our universe. We see many irregular galaxies that have no particular shape. It's probably what ours will be like in the future, which is amazing that we live in this time where we actually have a structured galaxy in the way it is. This is the solar system with Betelgeuse instead of the sun. So you can see all the inner planets are crashing into it. And everything kind of went haywire. All the gravities in this solar system, of these planets just went haywire. This is about 2 months a second. Okay, this is about 2 years per second. Wow, you can see everything just slowly become eventually sucked into this Betelgeuse, man. Wow. We will eventually, over probably, 50 to 100 years, maybe a few centuries, everything will eventually get sucked into it. It'll disturb its gravity enough to disturb it. So what we're seeing today, right, like the modern solar system, is only the product of billions of years of stability between all these things. Now, in the past, our solar system was very much more disorganized. But in the past, there were many more planets that smashed into each other. They became larger planets like the Earth. The Earth is a product of two planets colliding. Probably Venus, probably other planets, and a lot of them probably got sucked into the sun at some point. Probably the sun ate them up. Some of them got ejected out into space and never will come back. So what we're seeing today is the product of billions of years of stabilization. Relatively stable. Of course, at the end of the day, everything will eventually become particles, but that will be billions, perhaps trillions of years from now. So here's all the planets between the Earth and the Moon. The Moon's right there at the end. Wait, is that the Moon? Yeah, there's the Moon. So this is basically showing you the distance between the Earth on the very left and the Moon on the very right. And it shows us that all of the major planets can fit between the Earth and the Moon. That's how far away we are, or how small the planets are. And that's incredible. Look, even Saturn's rings. And here's a good image of how large the Great Red Spot is compared to the Earth. It's practically the size, or 2 to 3 times the size of the Earth. It's a gigantic storm. The winds of Jupiter can reach 1,000 miles per hour, even more perhaps, because there's very little friction on the planet. There's no surface. There's no solid surface, so it's going to be very. It's going to foster a very high, heavy wind environment. You can see some of the Saturn's rings are smashing into Jupiter right now. That's crazy. By the way, Jupiter, Saturn has a lot of moons, like Titan and Enceladus, and a lot of those are likely going to smash into the Jupiter as well if this was the case. But look how. Wait, are they smashing into each other? So this is about 30 seconds. So this is about 1 minute per second. Okay, speed it up a little bit. It's 2 hours, 3 hours. Wow. So the entirety of Saturn's rings had just got sucked into Jupiter. And what happens after a day? So this is about 2 days a second. Look at how fast Jupiter's spinning, rotating. Jupiter makes a full rotation about 9 hours. It is super fast relative to the Earth. And look at how small Earth is compared to Jupiter. Here's a supernova, type 1A. Type 1A supernova occurs when a white dwarf orbiting in a binary system with another star either merges or accretes enough mass that the white dwarf's mass crosses the limit. In this simulation, the star Sirius B accretes enough material until its mass exceeds the limit, triggering a supernova. Wow. So there's I don't know how to pronounce that, but But there's a limit where if you have a certain amount of mass, the star will explode. So this is a supernova close up in real time. So this is basically all the innards of the star just being spewed out into space. Those colors represent the different materials inside of the star. Different types of materials lead to different colors. And when you have when it's superheated gas, right, such as a plasma, you're going to have it light up. It's going to have enough energy to do so. That's absolutely amazing. In the universe, I think it's like every second, 1,000 stars go supernova. That's how many stars there are. Every second, 1,000 supernovae. Voyager 1 and Saturn. This is a gravitational assist. So you can see Voyager coming close to Saturn's gravity, getting a gravitational assist and spinning off in another direction. That's amazing. And remember, this was calculated by NASA beforehand. Like, we had to calculate this. We also did this with Jupiter, and then we actually have it here. Voyager 1 and Jupiter, yeah. So the same thing happened with Jupiter and Voyager. Voyager's coming in. You can see it comes in. And you'll see that it's going to use Jupiter's gravity to see how it speeds up a bit. There it is. See how it's turned a little bit and sped up? It did that first because Jupiter is before Saturn. It spun around Jupiter, and then it went around Saturn right after this. And that is incredible. And the NASA scientists were very close to this not happening. I mean, they had a very small window to work with. I mean, literally seconds. If they were off by even seconds, that would never have happened, and the mission would have went bad. Let's see if the Earth and the Moon collided. Wow, that is crazy. I mean, if this happened, the Earth would pretty much be toast. I mean, we'd all be dead. I mean, the Earth would survive, but we wouldn't. Life wouldn't survive. The surface would be molten. The surface would turn molten and probably stay that way for millions of years, until eventually cooled off again. And Earth and Mars collision. Oh my gosh. Now that's crazy. Jupiter and Earth collision. Jupiter's like, what was that? It's like a mosquito. That's crazy. The Sun and Jupiter collision. So that's how big Jupiter is compared to the Sun. Now that is crazy. This is 1 minute per second. It just gets vaporized. Gone. It's gone. Here's the Earth with 50 small close moons. Some of the moons closest to the Earth are torn apart by tidal forces. Others collide with each other or crash into the Earth's surface. Wow. The James Webb is in the Lagrange point. It's just in space chilling out. It's got solar panels. Whoa. There's the lens. There's the mirror. Wow. That thing is amazing. And it's just chilling out there in space, just floating away. Oh, there's Voyager out there. That's so cool. So in totality, we can see that James Webb it doesn't orbit the Earth. It's in the Lagrange point orbiting the Sun. Remember, this is like 1 month every second. Every second, a month passes. So you can see Earth is orbiting Venus. Wow, Venus gets close to the Earth. And Mars. Mars takes about 2 times as long to orbit. But you can see here, there's some times where Mars and Earth are very, very close together. This is in 2029. I believe in 2031, we'll be very close, I believe. Yeah, 2031, you can pause it. There it is. Look at that. Bam. So in April 2031, we will be super close to Mars. Look how close we are. And this is when most likely the next mission to Mars will be. Most likely we will leave Earth around here, around 2030, late 2030, get to Mars on like March, April, July 2031. That's going to be crazy. The Tesla Roadster that Elon Musk sent out travels out further than Mars sometimes. It's just a weird orbit. There we are. What a humbling perspective this is. What an incredible place we live in. Kind of transcends everything, right? Like this cosmic perspective transcends all of our petty things that we deal with every day, all the problems, all these things. Space, understanding space does something to make us feel like that these are petty problems, right? It kind of dwarfs these problems that we have in our daily lives. All the stupid fights and arguments we have. There's something grander out there, a bigger picture out there that we should have our eyes on all the time. But instead, we're so focused on what happens here in this little dot, right? But what a perspective this is. Amazing to be able to live in this world today where we have this ability to understand this. This is a remarkable thing to do, to have. So thank you guys. On that note, have a good day. Enjoy, like, comment, subscribe if you like this, and see you next time.